Good evening. Let's get started. 6 o'clock. We have some participation, over half. I hope others will join soon. Tonight, we have two discussions, right, left. One is about the floating point representation, which was supposed to be our tonight's topic. And other is exception and interrupt handling. It's mostly on the conceptual level, which will be the next one. So after that, these two, we will basically conclude our CS47 course after that. And tonight, I want to give you some idea and some conception about the registers. So we talked about these registers in the addition subtraction time, not very clearly, but definitely we used some component name register during division, digital division and digital multiplication logic circuit description, and but without giving some background of that specific hardware component. I will try to give some functional concept to you tonight, and before I go over to the floating point area. Um, and But this is like more like a conceptual. We'll study more on these registers construction hardware wise in the CS147. I just give you some functional specification description now, and just to give you the concept, what is a register as a component, and how it works. Okay, what's its function? So registers, in a sense, it is, you can say, like it is also a part of the register file. Remember, like register file you are using in MIPS assembly programming, and there are 32 different registers that you are accessing. So far to you, this register is nothing but some like data type to you. It is a storage. But in fact, there is a hardware component called register, which is used in the register file hardware implementation. Okay, so when I'm talking about that hardware component register, not the software storage concept as in the assembly program register, but they have this one-on-one relation, one-on-one hand-to-hand correspondence with each other. The register file in the MIPS register file, inside each individual 32-bit registers are these specific register component. So till before I share my screen, any question from any of you? Okay, so let me share my Jamboard with you now, and let me tell you what these registers really means. Video chat. Okay, so register is an hardware component, and we are dealing with in our MIPS lab, all this MIPS environment is a 32-bit register. But here, let me pick up our 8-bit register. Is an 8-bit register. Its storage so it has this 8. You can conceptually say that there are 8 bits stored inside this component. So this is the whole component. And inside it has some digital circuitry and all this stuff. That's okay. This guy is depending on it's a synchronous element or synchronous component, which means essentially it has a clock input. Okay, and it has some control signal called load. Okay, So let's talk about this one, load and clock, load control signal first. And okay, and it has something like reset. So reset, essentially what it does, it basically change the content of this register to all 0. Like if this guy is set to 1, then internal, whatever the content is, internal content become, all these individual bits become 0. That's the reset. Now, it has this, each of this bit. So usually we, at a schematic diagram level or component diagram level, we draw this register as this component. Like this is my clock, and let's say this is my reset, RST. This is my load, and this is my input I, which is, let's say for this case, it's a 8-bit input, and it has an output, let's say Y, which is also 8-bit output. So in this case, in this diagram, when we split up the bits showing it, this means usually like this. You have input, 8 individual bit input. This is my I. And this is my I here. And we have output, 8-bit output. For 32-bit register, it will be 32-bit output from here. So this is my Y. Okay, now, if we, let's say, on the input side, we have set my each individual bits to this bit pattern. Okay, this bit pattern, which is 0, 1, 0, etc. So what will happen if we make the load signal to 1, then all these individual bits will come and store here in one shot. Okay, so if I just want to give you a hint there, so let me so this guy will be replaced, all these things will be replaced. Replaced with this bit pattern. Okay, so this bit pattern will come into the storage, and that is in one shot, means within one clock cycle, within one cycle it goes into here. Okay, and this is what we called a parallel load. So parallel load operation means all the bits are loaded inside or stored inside this device together at one clock cycle. Now that means we can imagine there is some other type of load that must be, like, otherwise we would have called it just a load, not a special name, parallel load. In fact, there is something called serial load. In some of the register, we have more inputs, okay, more inputs. So it's basically something like, we call it a scan in, SI, scan in. And there is one specialized output also called SO, which is known as scan out. Okay, and usually in this case, instead of load, it has something like mode or M. Let's say M equal to mode. And let's say is M is 0, do nothing. Let's say M is 1, and usually it is like multi-bit. Let's say it is 2-bit. Okay, M is 1, then it is parallel load, and M is 2, it is serial load. Now what the serial load is, let's say M is 2, okay, and let's say you have a scan in. Let me use a different color. Scan in right here, okay, and scan out. Let me use another color. Scan out. Scan out is this one, okay. Actually, I take it out. Usually, scan in is related to the LSB, okay, and scan out is usually related to the LSB, okay, and it has, in this case, there are a couple of other instruction as well. What are they? RS is right shift, LS is left shift. Okay, so let me introduce them. RS, LS. Okay. Now what will happen here in this specific component? You want to load this pattern, right? You want to load 0, 1, 1, 0, 1, 0, 1, 0. So each clock cycle, we will scan into the device and then do a left shift, okay? So what we'll do is basically, let's go back to my original diagram where I have all 0 inside. Okay. Okay. And let me also do one thing, change the color of it. Let's see, the red is the overriding one, which is incoming into my register. Okay. Now, what I do in this case, in the mode 2, that is serial load, each clock I will send in one data, okay? So I will send in 0 first, okay? And M2, in that clock, what it will do, it will throw this out. It will shift these bits. C, Control C, why this is going, okay, going order forward. Going this. So in the scanning, it will shift towards the left and new bits come in. And then in the next clock, I will scan in this 1 into here. So what will happen? It will throw away this 0 and all the zeros are shift left. And 1 comes in here. So similar operation goes for the next clock cycle. So throw out, shift in, and then I shift in this guy. So you get the like general idea, right? What is going on in the serial load. So for the 8-bit loading, the complete pattern, it would actually need 8 clock cycle to do it. Okay, so that is called a serial in. So in this pattern fashion, you will just, like throw everything, and this guy will ultimately shift to here. This will shift to here. This will shift to here. This will shift to here, and this guy will just go in and bring shift and settle here. Then go in, shift and settle down here, go and shift here, and go and shift here. So that is the serial load operation. So parallel load, everything is loaded in one shot, one clock cycle. Serial load is loaded bit by bit from one side to another. Sometimes there are complicated registers which also can shift in from the MSB side to this direction, and also has other direction load as well. Okay, but that's a little complicated thing, but conceptually it's the same. Is a serial in, serial load of the register. And then the register has this shift, right shift, left shift capability also. Not all the component, not in the register file registers, they don't have this capability, but those registers in the multiplier and division circuit, those register hardware component has this capability, right shift and left shift. What happens in the right shift of left shift? Let's talk about the right shift from this pattern, right? So let's say in a clock cycle, we make it 1, right? So without anything special, if we don't have anything special on the register, in this clock cycle, when right shift is 1, it will throw away this guy and right shift every one of them. Oops.
So then that's the last clock cycle?
What's that?
Is that the cycle after it's loaded all of the bits?
Yeah, let's say we have that
right.
The bits, and after that we are trying to do a shift operation, right shift operation. So it becomes then question, what will become at this place, like at the MSB side? What will become? So in general, in less complicated circuit, this becomes 0. You can think that 0 is introduced at the MSB. Each right shift, a 0 is introduced. Let's say next clock cycle, we do another right shift. So this is thrown away, and this MSB is replaced by 0. Okay. But there are some complicated circuit as well. Okay, I'll come back to that one, but let's talk about the left shift. So what is happen on the left shift side? Let's say now After this, I basically turn on left shift to 1. So in that clock cycle, what will happen? From the MSB side, this will be thrown off and content will left shifted 1 bit. Now what happens to the LSB, the blank position? In normally simplified register, it is replaced with 0. Okay, let's say another left shift. So it will, this guy will thrown away, and we have will introduce a default 0. Okay. Now in a little more complicated component can be there, which basically has two different side input. Like let's talk about, or we can reuse the scanning here. Scanning LSB, let's say, and scanning MSB. And what are these? This data is connected to MSB and LSB side. And let's say I fix a 1 here. Okay, let's say what I can do, I can supply this data from externally from outside. So let's talk about this one. Okay. And I can fix, similarly, let's fix an external 0 here. Okay. So now let's talk about this shifting operation once more. Let's say this is my initial configuration. I loaded this data, parallel or serial, doesn't matter. I loaded this. And then in this specific special register, where I can actually control what I will insert into the LSB or MSB position. Okay, LSB or MSB position. Let's say I fix it to 1 and 0 respectively. And then I am trying to do a right shift. In that clock cycle again, what it will be doing, it will throw away this guy. Everything is shifted. And on the MSB, this bit will be copied. So one more right shift. This will throw away. Shift, 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 and this is copied. Now let's do one left shift at this point. Now I change this to a left shift. So what will happen here in this case, this will be thrown away. This will be shifted. And this will be copied, whatever that signal is. Okay. Question? So these are all complicated register and different concept, that shifting and all this stuff. And we'll check how to construct this in a logical sense with the logical basic logic gate that we learned, like NAND, NOR, and or those gates. We'll study it in the 147, how these components we can actually implement. Question? Nope. Okay. Now, 6:25. Okay, let's take 5-minute break. Why don't we take 5-minute break? And after 5-minute break, we'll come back with the floating point problem. Okay, and if you have any question also on the floating point representation.
Professor, actually,
Yes.
on your lecture,
Mhm.
the binary code of the D that you solved the example, you wrote the wrong, incorrect one. So just
Which
can you
one?
on the floating point, one of the example, the
Hmm?
D, I think you wrote it 1110.
D. Okay, I'll check it.
Yeah, yeah.
Which slide number? Which page number?
I don't know, but I know that it's about the part two of the video part two of the lecture.
Oh, okay. Can you
Okay,
find out what? Let's take 5-minute break, and can you find out which one? Which?
okay, okay. No problem. No problem. Thank you.
Okay, let's get restarted. Omid, did you find out which one you're talking?
Yeah, it's not in your lecture. It's in your video. The example that you solved it in the video, part 2, at
Okay.
9. I think it's a 9.
Oh,
At
can you send me an
9.
email? I need to review that.
Okay, okay, yeah.
Yeah, just send me an email with the timestamp, which video and what timestamp.
Okay, the video is part 2. Okay, I send you. Okay,
Okay,
no problem.
okay, please do that. Yeah.
Okay.
I see one question from Charlotte. Let me just share my screen. Charlotte asked that challenges section, double precision, what is that and why it is a challenge? Okay, that is not a challenge, Charlotte. Let me share my screen first. That is not a challenge. Challenge was this thing. Your underflow is a challenge, and underflow error, if it is like, it is means it is too small to be represented by the format, right? And this means your this underflow, this too small value, right? What it is controlled, like how small we can go, that is controlled by this fraction part, right? So IEEE 64-bit was recommended for that one. And in that case, you can go 52-bit of the fraction part. That means it's way too smaller compared to what the 32-bit floating point offers to us. Uh, does it mean it solves the underflow problem? No, there will be some values which will still which cannot be represented even by 64-bit data, even by 52-bit fraction part. That is the whole problem. But in general applications, the day-to-day applications, probably this is good enough to go with. This is like good enough approximation value that we can live with. Where it can give me trouble, very, very sensitive scientific applications or supercomputing, where you are actually computing maybe at the atomic scale, or maybe at the you are an astrologer who actually measuring something at the cosmic scale. And on at those points, 64-bit may not be enough. We may need to go to the 128-bit to 56-bit and so on and so forth. But that is very, very localized problems, very specialized problem. In our day-to-day computing environment, what has been found that 64-bit, that double precision value is good enough for us to overcome this underflow error. We don't run into frequent underflow error as much frequent we may get for a 32-bit values. Is that clear, Charlotte?
I guess, what is the bias then?
Oh, bias is this one, right? Your exponent value minus this 127 as in the 32-bit format, right? Is a constant bias of 127. Now is in the IEEE 64-bit format, this is 754 double precision format, your bias, that value, instead of 127, it is 1023.
Oh, okay, that makes sense.
Yeah, this value. This is always like assumed. It is not encoded within the bit pattern. It is just assumed that this 32-bit IEEE 754 floating point standard has this constant bias of 127, whereas the 64-bit, the double precision structure or representation, has a constant bias of 1023.
Professor, could you repeat why 64-bit? Because we started with the 32 bits. Because
Yeah.
it's too small. This is the reason that it's 64 bits?
There can be like underflow error is basically if a value is too small to be represented even with this 32-bit, right? So we have the smallest magnitude of 2 e to the power minus 33, about that part. If you use like all 0 LSB to 1 and exponent bit to all 1 exponent, no, not all 1, all 0 exponent bit, like exponent bit to all 0, fraction bit probably LSB to 1, everything else is 0, then the value you get, it is magnitude is more like 2 into 10 to the power minus 38. That's the value is. Now in your application, like when you are dealing with the real life problem, then this smaller magnitude can also be a problematic. Okay, so if you want to go beyond this smaller magnitude, then you need to move to the 64 bit, where you can go much smaller, like 2 into 10 to the power minus 308. That kind of precision you can go.
Okay, thank you.
All right, now let's do a problem here. So here, let's say I have a code which we haven't programmed much with the floating point, etc. But here it's very simple. Like if you can always consult your MIPS page, right? And then you can see that, let me, okay. We only use two of them, LWC1 and add-s. So LWC1 is this one. Basically what it tells that from that memory, that 32-bit pattern, you bring into that target register. So here we are reading from the variable on that level, means that word, store in this F1, and other is F2. And add s is nothing but is a single precision addition right here, which basically picks up two floating point register, add them up, and place the value into the target floating point. So that means in this case, it picks up values represented in F2 and F1 and stored the addition operation result into the F12. And then it's given that there is some syscall, this part, which is comment, also has a comment that it is to print the float value stored in the F12, whatever that bit pattern is. Now the question becomes, how do we solve this problem? And to solve this problem, we also need to know how that 32-bit pattern, what value it represents. Do you need to remember it? No, because second page actually gives you the format right here, right? You see the format? It's given the format already. So make sure that you can read through this page. Okay, informations are right there. So saying that, now all we need to do is turn these two patterns into bit and compute the corresponding values. So far so good. Like, you guys are with me so far? Okay, I believe you are. Then let's do this problem. Okay, now the first bit pattern, we are loading on the F1, right? So my F1 is C06 F8000, which means In binary, if we blow it up, it is 1, C is 12, right? Which is 8 plus 4. Okay. 0, 0, 0, 0. 6 is 0, 1, 1, 0. Then F is 1, 1, 1, 1. 8 is 1, 0, 0, 0. Then 3 zeros. So this is my 32-bit pattern. Now out of these, now this is loaded into F1. Now question is what it represents. According to the IEEE format, this is my sign bit. Okay, and next 8 bit will be my exponent. So this is S, this is E, and rest of them is my fraction. Okay. Now, that means what I can say for this case, S equals 1 and E equals, this is 8 bit, right? So 2, okay, let's see. This is 2 to the power 1, 2 to the power 2, 4, sorry, 2 to the power 1, 2, 4, 8, 16, 32, 64, 128, 128. So my E is 128 and my fraction part is whatever that is, right? Or I can actually discard these zeros here. And let me write it down. Okay. 1, 1, 0, 1, 1, 1, 1, 1. Right?
Okay.
That's my fractional part. Yes.
Can we write both of them var1 and var2 to the binary, then add together addition?
No.
Okay. And can I say why?
So basically, when you do a binary addition, you are talking about the integer value addition. So 2 integer value addition, and that won't give you the floating point answer. That's why all the processor needs a coprocessor which acts dedicated for the floating point computation. Now, how that works, if you are interested, this is more like a math domain problem. There are books available, like it is a C primer or something like that, math library. It's a floating point algorithm book. It is very, very like mathematics oriented topic. Okay. And frankly speaking, beyond my reach at this point. Okay. So that it has to follow specific algorithm, and that algorithm is implemented on silicon, on hardware as a floating point coprocessor.
Okay.
Okay.
Okay, got it. Thank you.
Now we simply apply that this thing, your formula, right? This is -1 to the power s. So your value -1 to the power s into what do we have? 1 plus fraction. I can write it down like this: 0.1101111 multiplied by 2 to the power e, which is 128 minus 127. Like it is coming from right from here. Right, coming from here, exponent minus bias. Bias is 127, and my exponent is 128 from this pattern, right? So, which means this is a negative number, -1. Okay, and then multiplied by 1.11011111 multiplied by 2 is 1.101111. Okay, now how we, so this is in base 2. This is in base 2. Base 2. Okay. Now, how we convert these guys? I know the answer is negative because we have this -1 multiplication component there. Now, what is the fraction part, value part of it? This is minus 2 to the power 2 to the power 1 2, plus 2 to the power 0 plus 2 to the power -1. So this is -1, this is -2, plus 2 to the power -3, 2 to the power -4, 2 to the power -5, 2 to the power -6, 2 to the power -7. Now use the calculator to do that. I have somewhat pre-calculated somewhere in my note. Okay, so this is 2 plus 1 plus this is 0.5 plus this is like 0.125 . So this is 0.5, 0.125, then 2 to the power -4 is 0.0625, 2 to the power -5 is 0.03125. Basically, you are just dividing each step by 2. Then it is approximately 0.015625. Okay, and this one is approximately about 0.00782125, which boils down to about 3.742185. Okay. Now we need to do for the next one, which is under the F2. So F2 will have is a pattern of 0400A8000. Okay, so at this point, what I'll do, I will open up the breakout room, work with your peers on to come up with the value of this pattern. Okay, fractional value of this pattern. Breakout room for 10 minutes. Move to, just give me a minute. Okay, 10 minutes. Go to your room and solve this problem. Okay, I think time is up. Let's have everyone to get back. I believe. Yeah, I believe everyone is back. Anyone wants to give me an answer? What's to find out what's that F2 will be loaded with?
Is the answer negative 1.628125?
F2?
Oh no, F2 is 2.1640625.
Yes. Right, exactly. I hope everybody else has this value, or otherwise you probably has some issue there in the calculation. The answer for the F2 will be loaded with 2.1640625. That means at the end of the day, your add S, let me share the screen. Which one I'm sharing? Share. Okay, so at the end of the day, your this part is minus 3.7421875. So this is this part, and the other one, the F2, will be loaded with 2.164.640.625. So now we are basically adding these two values here. So if we use that add value, we'll get something like minus, so this result will become minus 1.578125. Is that the answer you are talking? Did you get this answer? Minus 1?
Not quite. Did I
That's what I got. Maybe check the calculator.
Alright,
Input.
yeah, probably that then.
Yeah, this too. I think, yeah. Let's rain check. Like this is 12816. Right. So this is 5781.
Oh yeah, it was a typo. That's right.
Right. Now, if I add back I'll get this one. So, yeah. Okay. So that will be printed on your Mars terminal. So this is how you do it. Like there can be other way of dealing with that. Maybe like a snippet of the memory is given, and to say, okay, this is a big endian memory, and you're accessing this specific address and loading it into the floating point register. What is the value we are loading? So that kind of problem you can also think of, like given a snippet of the memory itself, and given you the endianness, from that approach, you see what is the bit pattern is loaded into the register, then break it up with respect to the IEEE 754 format and calculate the value like what we did right now. Question?
How would you convert that value back into a floating point number?
Okay, this one, okay, this value into the bit pattern?
Yeah.
Yeah, that's a good question, and I don't know. I need to figure out. You guys search in the Google and see.
Okay.
So that means I am not definitely going to give you that problem. Given a floating point number, how you want to convert into the binary pattern? That's a good question. Let me also try to figure out. Okay, any other question?
I was wondering, like, in the, you know how like you got the binary representation of the number, like with the decimal in there, like after you converted it from the floating point representation.
Mm-hmm.
At that point, if you just did like addition using, I guess, like math, would that like
Right. Yeah. So basically, yeah, maybe like we go with, we have a 1 there. So definitely it will be something like this bit will be on, like we need to have this term, and 0.5 means we need to have this term, right? And then 0.07 would be like, so basically we try to see, yeah, we can make an algorithm out of it, like step by step, as you said, you're correct. And we know all these values pre-computed, like 2 to the power 7, etc. And we can just keep on subtracting the values from this target value till it becomes 0, or we cannot go further. Yeah, that can be one way. Yeah, we can try this. Yeah, try it, and yeah, let me know. I'll also try it, try to find out what is going on. But okay, on exam, not that question. It is just for our fun.
Okay, thank you.
Okay, anything else?
Professor, we don't have a class on Wednesday, yeah?
No class on this Wednesday. Enjoy your Thanksgiving and whatever holidays you want to spend with. I hope everyone is writing the report now and be done with before the holidays, before the break. Don't ruin your break over the projects. That's my motto. Though my deadline is after the break, yeah, I was thinking to like have it before that, but somewhat I gave it afterwards the break. I hope it will help some of you, but I wish not.
And Professor, another thing, final exam from the beginning or?
Yeah, it's comprehensive everything.
Okay.
Yeah, we'll talk about more about final exam on this coming Monday when we come back from the holiday, and also watch out for the announcement. There will be some information on the final exam. Yeah, and we'll have 2 review sessions after the Monday. Then we have 2 more classes. On those 2 classes, we have review session. And yeah, I'm still working on your final exam paper. I haven't fixed it yet, so hopefully we'll come up with something. Okay, if there is nothing else, then let's good night, have a good break, and see you all on Monday.